Fine-grained image classification is one of the toughest challenges in computer vision. It's the task of telling apart objects that look almost identical, like two bird species, dog breeds, or car models. But when shapes, colors, and textures are so similar, how can a machine learn to see the tiny differences that even humans miss? That's where a new deep learning approach called CFD-FIAF steps in. It blends both the spatial and frequency domains of an image, helping I see not just the big picture, but the tiny details hidden within it. In fine-grained visual classification, or FGVC, every detail counts. A small curve on a feather, a stripe on a car, or a subtle change in fur texture can mean the difference between one class and another. Traditional image classifiers focus on global structure, the overall shape, which works fine for broad categories like bird or dog. But for FGVC, that's not enough. The challenge is twofold. Different classes look almost the same, while the same class can look very different depending on lighting, pose, and background. So we need a way to capture high-frequency details, the fine edges, textures, and patterns, while still understanding the overall structure. The CFD-FIAF model, cross-layer, frequency-spatial domain, feature interaction awareness. Fusion enhances fine-grained image classification by combining high-frequency detail recovery, frequency attention, cross-layer fusion, and consistent prediction alignment. 1. Frequency Domain Feature Complement Module, FFCM. As deep networks downsample images, they often lose sharp edges and subtle textures. FFCM restores these high-frequency details by reintroducing the fine structures lost during this process, improving edge clarity and texture precision. Real-world impact. Ideal for detecting small surface defects in manufacturing, subtle differences in bird feathers or car designs, and microscopic irregularities in medical images that standard models might overlook. 2. Frequency Domain Feature Awareness Module, FFAM. FFAM helps the model focus on important frequency components at multiple scales. It balances global low-frequency information, like shape and color, with local high-frequency details, like textures and patterns. Real-world impact. Enables AI to tell apart nearly identical species, distinguish authentic from counterfeit products, or identify early disease markers in tissue scans by analyzing subtle visual frequencies. 3. Graph Convolutional Network. Feature Fusion Module, GCNFFM. Different layers capture features at varying granularities. Shallow layers see edges, deeper ones understand object semantics. GCNFFM uses graph convolution to fuse these layers intelligently, allowing them to share context and strengthen feature representation. Real-world impact boosts accuracy in complex scenes like satellite imagery, where combining fine textures and global shapes is critical. 4. Prediction Consistency Distillation Loss, PCDL. Predictions from different layers can conflict. PCDL enforces consistency by aligning multi-scale predictions, improving stability and coherence. Real-world impact enhances reliability in medical diagnosis, autonomous vehicles, and quality inspection systems where inconsistent outputs can lead to critical errors. Together, these modules let CFD-FIAF see both the big picture and the smallest detail, delivering sharper, more consistent recognition across challenging fine-grained tasks. So, does it work? Yes, impressively so. On 4 benchmark fine-grained datasets, CUB 202,011, NA birds, Stanford cars, and Stanford dogs, CFD-FIAF, achieved state-of-the-art results. But that's not all. When tested on a specialized bulbous fritillaria dataset, a traditional Chinese medicine plant with nearly identical subtypes, the model reached an astounding 99.8% accuracy. That means it can detect the tiniest visual cues between similar herbal species, a breakthrough for medical and biological classification. By combining the frequency and spatial worlds, CFD-FIAF lets deep learning models see with sharper, more detailed eyes. It bridges the gap between local texture and global form, pushing the frontier of fine grained visual recognition. From identifying bird species to authenticating medicinal herbs, this new framework proves that sometimes the smallest details make the biggest difference.